Hi, so thanks for coming. So I want to talk about how using a reactive communication protocol can completely change the way you do your edge architecture. First, sort of in the general sense, and then based on experiences we had at Netflix, and then a little bit about what I'm doing now. So who am I? I'm Rylan Degden. I'm the CTO of Nnetifi. Earlier this year, like for the last 4+ years, I was a member of the Netflix Edge platform team, where we built a lot of the technology that I'm going to talk about. And I've been a contributor to RSocket, RxNeti, so I've been in the sort of reactive space for a while. So I wanted to start with a quote from Alan Kay, which I found really interesting. If you don't know who Alan Kay is, he was the inventor of the small talk language. He spent most of the 70s Xerox PARC sort of inventing the future of personal computers. And interestingly, I found out his 1969 PhD thesis was called The Reactive Machine, so nothing new under the sun. But he said this, I was listening to a talk by him, and he said the internet was so well done, most people think of it like a resource, not something that people created. And the web, in comparison, is a joke, right? The web was done by amateurs. So, I mean, I was surprised by that at first. So what did I actually mean by that? But I looked into it a little bit more, and I started to agree with him, right? So this is, he'll say this, like you go to the Wikipedia page for the Logo programming language, and like what did the inventors of Wikipedia not understand about computers, right? Like you're visiting this page on a computer which is capable of so much, and yet it's just a wall of text, right? There's no interactivity. Why can't you compile and run Logo code on the browser, right? Everything is a computer. But the web was designed to transfer textual information back and forth in one direction. But what worked back in the 70s doesn't really work today. It seems odd, right? There's huge differences about the world today. There's massive mobile device growth, so everybody is walking around with a computer in their pocket that is vastly more powerful than the supercomputers of the 60s and 70s. And not only that, but these devices are increasingly connected to the internet. Your phone is always on, it's listening for information. Why do you have to go and pull a service over and over again to find out what's changing in the world around you? And all these things combined, we've come to expect some level of real-time interaction. We don't want to just go and refresh our Facebook page and see what our friends are doing. We want the information to be sent to us. We want to be notified. And all this is sort of none of this is really possible with the technology that underlies the web because it wasn't designed for this interactivity. It was designed to share text. So there's all these different experiences that people are creating that we want to use, whether it's sending images from phone to phone, streaming video over the internet, interactive virtual reality, video games, you name it. And all those experiences rely on this communication layer. But the problem is, everybody built these experiences on top of an old foundation, something that was designed before any of this stuff was even imagined. So if you were going to go out and design something today, would you use an old technology like HTTP, or could we possibly do better? So the fundamental problem is communication between applications is complicated and it's inefficient. Errors are hard to handle. Once we send out a request, it goes off into the ether, and we can't cancel it, we can't do anything about it, we just have to wait for a response. And on the other side, a server cannot tell a client, like, hey, stop sending me a request, I'm not actually able to process it now, I want to go offline for 30 seconds and do garbage collection, so just hold off for a second. And all of this leads to the problem of configuration. So you have to constantly be monitoring your services, configuring them, and this configuration is usually static, despite the fact that every service out there is dynamic, right? Load changes throughout the day, things come and go. What you really want is something that adapts to those changes in real time. But does it really have to, is that complexity sort of fundamental to distributed systems, or is it just a consequence of design decisions that were made decades ago? So a really good example of this is the mobile phone, right? Early mobile phones were essentially landline phones in mobile form. There's not really any innovation there. They took the buttons and put them on the phone. And they pretty much stuck with that. And various iterations sort of tried to add a screen to it, and they started to add more buttons. Somebody thought, well, if I just add more buttons, then it's going to be easier to use, right? So I can add more and more buttons. And then around 2007, somebody at Apple had a different idea of how to do things. And from that time forward, mobile phones have looked vastly different. And that's just sort of a process of discarding old decisions that are no longer relevant and trying to find a new way forward. So sort of the thesis of this talk is that it's time to change the foundation that we use for communication between microservices. I'm picking a little bit on HTTP, but it's not really just HTTP. But what we really want is a new foundation that is more performant, more secure, makes things cheaper and easier, faster time to market. And all that is possible through the reactive programming model. So just to make this a little more concrete, I want to talk about this sort of thing I mean here. So this is sort of a typical scenario. You have a bunch of mobile phone users, and they want to make a request to some back-end service. All right, they've got the request ready. Good old Tomcat is waiting there to receive this thing. So it's sent out off into the ether, gets routed to your Tomcat server, but there's a problem. You just received way more requests than you thought you were going to. You're not ready to process them all. So you're overloaded for the minute, so you've got to respond with HTTP 503 or something that says sort of back off and I'm not ready for this information. But you don't really know when you are going to be ready. You just know that at some point in the future you'll be able to do this, but just not right now. So you have to form a 503 response, send it back. So users get the response, and now they have a problem because you didn't tell them when you were going to be ready. They don't know when you're going to be ready. They don't even know where the next request they send is going to be routed to. And so suddenly you have all these problems of distributed systems that we've probably all dealt with before. You need to make a decision, like, do I retry this request? If so, how long do I back off? Do I need to do exponential back off? Do I need to coordinate retries so that I don't get the thundering herd problem where your entire customer base is retrying requests at the same time? And believe me, we ran into all these problems at Netflix. And then, in some ways, the worst of all of them is the configuration aspect. I mean, you have to set up, if you're going to add circuit breaking, you have to configure that circuit breaking. Somebody has to sit there and constantly update the configuration because microservices behind the scenes are coming and going, being scaled up and scaled down, and nobody really has the complete view of the system. And so this, if you were happy with that, great, but Alan Kay is really disappointed with you because he comes back and says, hold on, the internet is actually really good, right? TCP is a full duplex bidirectional protocol. Everything is connected. We can send messages back and forth. What? Why can't we do better than this? So I want to go back and sort of reimagine this scenario if we were trying to do things a more reactive way, right? So first of all, everything is a stream, right? Nothing ever receives one request and is out, right? Everything is getting a stream of requests. So first of all, let's keep that element of TCP, that everything is connection-oriented. You want to model this as a stream of connection. So everybody sort of connect together, and we have this stream where we now send messages back and forth. And then let's do one more thing. The problem we had last time was that we didn't know whether the server was ready to handle the request or not. We just had to send it off and sort of hope for the best. What if we reverse that and now take advantage of this bidirectional protocol and have the server send the clients a message saying that he's ready now to receive 2 requests from each of them? And keep in mind that because this is connection-oriented, the server knows exactly who's connected to him, and he can distribute this request ends across everyone who's currently connected to him. And if he happens to want to garbage collect, he just stops sending them out, wait till the requests die off, do your garbage collection, and then start sending them again. Okay, so your customers now have gotten the piece of information they were missing before. This server is actually able to handle 2 requests. And no, it's not just request response. You can do a stream of information. So I want to stream 2 pieces of information out, which might just be part of a much larger or infinite stream of data. That arrives at the server, and now, well, we already knew he was going to be able to handle it because he told us so. Yeah, And then now Alan Kay is much happier because we're actually taking advantage of the fact that everything is a computer. All right, let's look at another sort of scenario. So you have all these, you have devices out there. Maybe you have a VR device, a mobile phone, a web browser. And in the back end, you have some sort of service that you want to communicate with. And then you have a developer sitting there who wants to interact with the system to know what's going on, capture metrics, and analyze the system. And so how do these things typically interact with each other? Well, if you're using HTTP, there's really only one thing you can do, and that's send requests to the server. So you can send a request from your phone. You can send a request from a web browser or a device. And someone sitting there trying to understand the system can sort of query what's going on, but it's got to be put in a database somewhere and then later on capture. So you basically have to capture all the information that's coming in and then query it later. I mean, that's all right, but it's a little bit boring, right? Alan's starting to look a little bored here. So let's think about what are the other modes of communication that we could actually do in this system that are not currently easy or possible. Well, of course, we can do the server request response. But with a bidirectional protocol, you can actually have the server send messages out to your clients. You can have a server send an update to a mobile phone saying, hey, there's a new message ready for you to receive, or to a web browser, or even to somebody who's interested in metrics that are happening about the system in real time. They can be updated as events that they're interested in actually happen. And then the other thing is we shouldn't limit ourselves to one mode of interaction, the request response. Again, why not open it up and allow streams of information to be sent back and forth? And then it's not just servers who should be able to handle requests, right? How come this guy can't interact directly with customers on the other end with devices? So say you're trying to debug a complex problem. You just want to sort of connect to the system and handle one request on your laptop and step through what's actually happening. Well, why can't you do that? You send a request for one request out. That's the only thing that will ever be sent to you. Everything else will go back through the floodgates to the rest of your service architecture. Or why can't I point to a single customer out there who's having a problem and say, can you just start sending me debug logs from your phone? And then the third piece of it is, why can't, through the same architecture, all these people are connected in over a persistent connection. Why can't they talk to each other? Why can't I send a request from my mobile phone to my web browser to my devices? It's all possible over the internet. It's just that the abstractions that we've layered on top of it make that very difficult. And so the full picture of things is actually a lot richer than we limit ourselves to. And that makes Alan really happy. He's kind of raising the roof there. So. All right. So this protocol that we've sort of been imagining does actually exist. We built a lot of it at Netflix. And it was sort of an evolution of the Reactive Streams effort, which was a collaboration between Netflix, Lightbend, Twitter, Pivotal, a bunch of other people. And sort of an effort to define a common interface for streaming data across an asynchronous boundary. That's sort of caught on. It's now actually in the JDK9 Flow API. And so the next evolution of that was the concept of RSocket, which is if Reactive Streams abstracts an asynchronous boundary, RSocket abstracts things over a network boundary. And it supports all the things that Reactive Streams supports, so backpressor, flow control, cancellation of things that are currently in progress. And that is an ongoing collaboration between Netflix, Facebook, my company, Nnetifi, and others. So, okay, great, but how did we arrive here? How do you actually use this stuff in practice, and what does it mean for your edge architecture? So I wanted to take a step back and sort of look at the evolution of this stuff within Netflix, how we arrived here. So I mean, most of you are probably familiar with Netflix. It's a streaming video provider. We deal with huge scales. I think it's sort of 10% of upstream traffic during peak hours and 35% of downstream traffic in North America. So Netflix cares deeply about the edge. And so what do I mean by the edge? I think this is a good way of looking at things. So on the outer layer, so the most widely distributed layer is the devices. So it might be phones or browsers or people who are trying to make requests into your central network. And slightly less widely distributed is your edge layer, just sort of everything in between the devices and your back-end services. And then the more centralized piece of it is your cloud or data center, where you're actually running your services. So let's rewind about 10 years. So this is what the Netflix API essentially looks like, and still looks like. You've got a bunch of devices out there, and it's like a giant funnel, right? Everything actually goes through a single API gateway and then gets fanned out to all these microservices behind the scenes. And I mean, back in the day, it was a pretty typical REST API. I mean, everybody's probably written stuff like this, but if you wanted to retrieve information about a movie, you could call /catalog title. Catalog people might get you actors. And sort of all these different devices had to consume the same REST API, which is then called into some Java business logic and then synchronous HTTP requests out to the microservices. But I mean, it wasn't long before we started to run into some problems with that approach. First of all, it's really hard as a centralized API team to decide the granularity of your REST model, right? Different devices require vastly different information to actually be able to render their screen. And so we ran into the problem that some people needed different information than others. Some people needed to make dozens of these requests, while others could do with one or two. But for the ones that needed to assemble multiple requests, we're sort of forcing that cost to be paid in the worst possible place in your architecture, which is on the mobile device itself. So especially if you have requests that depend on one another, you have to sort of pay the cost of WAN latency multiple times as you try to assemble a single piece of information that you need to actually render the screen. And the other problem with this is the poor development velocity. So if UI teams want some new information to be returned from the back end, they have to go to the API team, figure out sort of which microservices are responsible for that information. We then have to go to those teams and ask them to add it to their API. Then we add it to the centralized API. And finally, everything has to be sort of deployed together. So it slows down the cost of the speed of iteration. And the third problem was there is no fault tolerance. So around 2012, we did a big sort of reimagining of the API. And this was sort of the origin of the Netflix Edge team. So we took the old REST API and we decided, well, if we can't design a single API that's suitable for all devices, why don't we let the UI teams actually write the API that they want and then present a common API using a reactive programming model to let them pay the cost of this composition on the server side and form exactly the response that they want to receive. And this is sort of the origin of Arc's Java. We created this reactive Java API to allow people to abstract away the concept of threads or asynchronous programming and just let them sort of compose streams together in a way that they didn't have to worry whether the underlying request was going off box or what was actually happening behind the scenes. It's all the same to them. They get an observable back. They can flat map over it or map composed data together and just serialize their response. And in addition to that, we added the Hystrix layer. So this is also the origin of Hystrix. So we decided things are changing behind the scenes. Now we can't really predict the calling patterns that we're going to have because people deploy these sort of endpoint scripts dynamically. And so we need some method of protecting the back-end services from bad calling patterns, and hence Hystrix circuit breaking. And so this is sort of what it looks like in context. This is a picture I'm very familiar with because I was on the hook for maintaining that central piece of the Netflix Edge, the central part of the funnel, the API that calls out to all the microservices. So, I mean, that worked great for a while, but then things started to change. So the Netflix Edge started to grow, right? I mean, the beginning of 2012, we had maybe 25 million users. We were just in North America and maybe a little bit of Latin America. But then fast forward 5 years, Netflix has over 100 million users. And to make matters worse, we went global last year. So it suddenly opened it up to traffic from regions we had never experienced before. Whereas that inner service layer is still sort of located in 3 regions, 2 in the US and 1 in Europe. So now we had another new problem, which is that customers in India have a pretty poor experience when they're using Netflix because their request to be fulfilled actually has to go all the way back to another region elsewhere in the world. So what to do about this? I mean, the world is changing around you, but the architecture still roughly looks the same. So something needed to be done about this API. We're sort of starting to run into problems on every level. Firstly, these dynamically deployed endpoints, which we sort of envisioned would be little scripts that composed a bunch of observables and then spit out a response. Well, people started to write applications there. I mean, give them an inch, they'll take a mile, right? Like there's thousands and thousands of lines of code, and they started to have dependencies among one another. So we had to come up with ways to dynamically deploy scripts that depend on other scripts. And then we run into situations where some logic, like A/B logic, might be very common to a lot of different scripts. And so when that team wants to deploy their code, it means reloading in prod sort of like 70–80% of the bytecode that's actually out there. And that comes along with jitting problems. We got to the point where every time we would deploy one of these shared modules, that we would see an SPS drop in prod. And the other problem was that we made the choice of this JVM language runtime, which offered us a bit of flexibility, but mostly ended up settling on Groovy as a language to write these scripts in, which not everybody was happy about. So a lot of people decided, hey, why can't I write these scripts in Node or Python or another language that I'm more familiar with? What's actually stopping that? Well, it's all running on the JVM right now, so that's tricky. And the third problem is this fault tolerance layer, because as more and more microservices come online, more and more configuration has to be done, right? Like, and the way they interact with each other becomes more and more complicated. So the settings that you decide on one day for your circuit breaker are maybe not valid the next day after they release a new feature, or a different team decides to shift over to calling a new API. Suddenly the traffic doubles and you have to reconfigure everything. So it ended up becoming more and more of a burden to maintain all the configuration knobs and dials that go along with circuit breaking. And then the other problem is that, again, as the microservices grow, we had a sort of a fat jar model, fat client model, where they would hand us a client and didn't necessarily expose a reactive API to us. And so we had to bridge the gap between blocking APIs and asynchronous APIs and pay that cost on the API layer. And that's, I mean, you can do that to a certain extent, but as you start to handle more and more traffic, you start to wish that everything was asynchronous. So what is the solution to this problem? Well, the solution that we sort of came up with in the context of this diagram is to push more functionality out from this centralized cloud out to the very edges of your network, so as close as possible to customers, to try to distribute this giant funnel so not everything is going through one centralized API, but you can actually do a lot at the edges of the network. And so in this architecture, that corresponds roughly to cutting this thing in half. Fortunately, we made a really good decision with the reactive programming model, because that hides not just, this is the brilliant thing about reactive programming and reactive streams, it hides not just asynchronous boundaries, but network boundaries. When you make a call and you get an observable back, you do not know whether that call was handled on the same machine or another machine. So it's a very natural thing to cut that in half over the reactive programming model. And this is basically the origin of our interest in RSocket. And so the plan then was to cut this thing in half and then distribute to a broader set of regions this set of scripts that formerly lived in this centralized API layer. Run those on containers with the additional benefit that we lose that dependency on the JVM, and they could equally write their scripts in JavaScript, Python, or Java as they pleased. And then the back end of this thing looks more or less the same, except everything is now communicating over a reactive network boundary that imitates the reactive programming model that they were previously receiving. But then, I mean, there's a little catch to that, which is that there's all this platform functionality, right? There's all this infrastructure that lives back there in the mid-tier, that suddenly these guys are out in the edges of the network, and they don't have access to that anymore. So things like discovery and load balancing, we had all this stuff written in Java. We didn't really want to have to rewrite it all in every language that anybody wanted to use. But fortunately, there's a good way to handle that problem once you settle on this reactive networking protocol. So let's look at what the edge might look like using like RSocket. So somebody from one AWS region wants to connect in. Instead of connecting to the backend service, they connect to this edge router. And the edge router is responsible for connecting it to the service in the region where the request is meant to go. So on the other side, the server also connects into this edge router. And the routers form this worldwide network of information flow, of virtual point-to-point connections that allow you to sort of seamlessly connect anywhere that you want to send the request to. So from the perspective of this user, they connect it in, they say, I want to talk to this service, and it gets routed there invisibly to them. And now we can also do cool things like sending over that same virtual channel, we can send streams of information to the channel and receive streams of information back. We're not limited to request reply anymore. And there's more cool stuff we can do, right? Instead of having a client-side load balancer that has to go out and discover who's available in the network and then assemble a list of all the possible addresses that could fulfill that request and then load balance from the client side, we can build that into the fabric of this edge network. So we worked a lot on load balancing technology that is built into the edge. In addition, it can take advantage of, like the first example I gave, the additional information that it's receiving from these servers, because the servers are now able to signal whether they're actually ready to receive requests or not. And so you can do interesting things with shifting traffic around. And so those endpoints that previously lived on the API server and were written in Groovy can now be distributed to the regions in which you're in. And so the edge router can know if this service is destined for an iOS endpoint, routes it to the local regional iOS endpoint, which then does the fan out to all the backend services, assembles the request, and then returns a single response. So you don't have to pay the cost of all this deserialization and assembly of responses on the mobile device. And in addition to that, I mean, there's other cool stuff you can do too, right? Now you can start to feed this into your data pipeline. So, I mean, part of the reason that Netflix is 10% of the world's upstream traffic at peak is that we emit so much data, right? Everything the user does emits a stream of data. As you're watching a movie, you need to know where you are in it, how you're interacting with everything. That no longer has to get funneled through sort of a central API server, but it can be sent over this virtual point-to-point connection to a Kafka server, and we can actually do back pressure so you don't overwhelm the Kafka cluster. And it doesn't have to be unidirectional. We can ask for what we need. So you don't need all the information all the time, right? There's a lot of times where you only need something when you're debugging a problem, and in 99% of the cases, it's actually going to be thrown away. Well, now we actually have a channel back to that phone where we can ask for the information that we want when we need it. And again, yeah, now Alan is kind of impressed. He thinks that's cool. So, so a group of us at Netflix thought there's so much potential in this stuff that we sort of formed our own company, Nnetifi. And what we want to offer is this reactive edge network, but as a service. So it's a globally distributed edge network that anyone can plug into. And it offers all of these infrastructural things sort of within the fabric of this edge network. So discovery, load balancing, resumability, which becomes important with mobile phones where the connection can come and go. You want to know that when you send a stream of information back to them, they're not going to suddenly drop their connection and lose all that data. So we cache with a limited amount of caching because of the request end. There's only a small window of things that you need to cache. We can sort of make sure that the next time that they log in and are able to receive it, they can resume the exact stream that they left off. And then because everything is this virtual point-to-point connection, you can do cool things with encryption, authentication, because two ends of this connection can agree on a private key amongst themselves, sort of without the knowledge of the intermediate edge router. So a virtual connection between a service and a phone can have an encrypted conversation unbeknownst to Nnetifi, or nobody else could possibly peek into this, even though it's traveling over the public internet. And then another core principle is this idea that it should be self-healing. There should be no configuration required, right? Because there's more information available, we can automatically decide the best routing decision. If an AWS region goes down and you have the same service available in another region, we can seamlessly shift traffic to that region because it's constantly looking at the best way to minimize latency across all available service providers. And it's not necessarily limited to API calls. So, and this is what it would look like in sort of like more of a data pipeline model. So you send a bunch of stuff in. It back pressures when you're not able to, if your Kafka cluster dies, you're not able to handle the request. It'll send back pressure so you can actually buffer data on the device until it's ready to receive again. So the advantage of this way of thinking, you get this reactive programming model. I'll go into that in a bit, but everything becomes simpler when you can just model the network as a stream of asynchronous events. And then you're not limited to TCP either. I mean, this reactive RSocket is not dependent on a particular transport. So we can use a really cool transport like Aeron in between these edge routers. And at the very ends, we can use WebSocket or TCP or whatever happens to be available on that device. But you sort of benefit from these high frequency transports in the interim. And then it offers, because it's reactive stream space, it offers the guarantees of reactive streams. If you send a series of messages, they're going to arrive in the same order. We're going to guarantee that it gets there or it will fail. And then the security stuff. And then the load balancing I was talking about. The guy on our team, Steve Guri, who wrote a lot of the load balancing stuff, wrote the load balancer for Finagle. And I think he was going to talk here, actually, but he couldn't make it this time. But I highly recommend you have a look at his talk. But predictive load balancing is a whole thing unto itself. And the consequences of this is what simple things are simple, right? This is what it looks like. If you want to make a request, you just say, send a message. You can do on next, do on error. You can flat map. You can compose streams. Everything is just reactive streams, and there's no callback hell. Versus, some other people do parts of this, but it becomes very complicated to actually compose things that are happening. You need to maintain local state, and it quickly becomes a nightmare. So we'd love for people to get involved. A lot of what we're doing is being worked on in the open source. RSocket is in the open source, our SDK. Please check it out. We have Java and Android right now. We're working on iOS, C++, and JavaScript. Facebook has contributed a C++ reactive streams implementation and a JavaScript implementation. We have another one at Netflix. So the sort of scope of RSocket is starting to grow day by day. So the SDK is what would allow you to plug into this edge network. That gives you sort of bytes back and forth. And then on top of that, we're building this Proteus, which is sort of an RPC abstraction on top of that. So it allows you to write an IDL in like a protobuf or other languages not restricted to protobuf. And then essentially define your services in that IDL. With a click of a button, you can compile all the code you need to actually deploy and run those services and have them talk to each other. And you can model streams or request reply or fire and forget. You sort of get all the richness of RSocket communication, but it's typed and defined in this IDL. So yeah, that's all I had. Thank you. Any questions?
So could you say a little bit about what role you guys are playing in this with RxNeti? I noticed you made a number of contributions recently there. Maybe you can illuminate a little what you're working on with RxNeti, where you're going to go with that.
So yeah, the problem with RxNeti, it was written using RxJava 1, which doesn't support back pressure. And so in the meantime, the folks at Pivotal had created Reactor Neti based on Reactor Core, which does support back pressure. and it sort of offers a very nice API, reactive API on top of Nneti. So the idea between the recent commits was to try to align on that same reactive API, sort of take the work that they'd done, but port it back to RxJava, mainly so that it's usable on Android, because the reactive stuff is Java 8 only, whereas RxJava, it has gotten more of a following in Android, and so it's committed to supporting Java 6 for the foreseeable future. So that was the idea there. And then aligning on that same reactive API on top of Nneti makes it much easier to implement the RSocket bridge. So the RSocket implementation looks almost identical now for Nneti or Reactor, depending on whether you're working in a client or server context. And then, I mean, there's other APIs in the work, like the Aeron stuff, it's sort of a work in progress, but it's not limited to Nneti. Other transports are certainly possible.
Just curious how you see this in comparison to gRPC and GraphQL. They're both kind of interesting. I mean, they're different use cases, but curious how you see how any of these relating or being totally different.
Yeah, I mean, so GraphQL, Netflix has something very similar to GraphQL called Falcor, if you're aware of that. But at Netflix, we're actually doing Falcor over Reactive Socket. But it allows you to add a streaming response to that. So you can stream data out and improve like the initial response time. But you can still have that sort of rich graph modeling language. And gRPC, in some ways, did a lot of good, but they decided not to opt into the reactive programming model. So what you get is callbacks, essentially, even in the asynchronous API. And so we're really trying to model this as a reactive. The base layer should be reactive, and then everything else can be built on top of that. It's much easier to go from an asynchronous API and say block on it than to go from a blocking API and make it synchronous. And then because everything shares the same common contract, this RSocket interface, then it's much easier to write generic functionality that you can compose together. And that's roughly how this edge routing network works. It routes on generic RSockets, whereas gRPC is a little bit more tied to a particular transport. This is designed to be more generic.
Can you say a little bit about what's your business model going to be? Is it going to be something like a Kafka Confluent type scenario, or?
We intend to charge sort of like a tiered model based on how much traffic that you want to send through the system, or if you want to run it sort of in your data center, then enterprise sort of model. But roughly, the idea would be charged like by the amount of traffic that you'd like to send through, like the amount of connections that you want to maintain.
And you wouldn't be putting up any of the infrastructure? It would be more just using the software?
For a user?
I mean, you wouldn't be hosting any of the edge?
No, I mean, it's hosted in the cloud, yeah. I mean,
Okay.
Right now it's hosted on Azure, but it's also kind of agnostic to the cloud provider.
Great, thanks.
Yeah, so it's ready to try out, so if anybody has an interest, then see us afterwards. Robert and Greg over here are also from Nnetifi. Great, if there's no more questions, then thank you.